In this section, we're going to take a look at modeling with systems of first order ODEs. Now, a quick note before we start here, because we're missing some techniques, we haven't seen them yet, this section really only introduces the concept of systems of linear ODEs, first order linear ODEs. We're going to see how to solve them in later sections. And I say sections because there's actually multiple ways of solving these, and we'll see different ones in different sections. All right, so let's say you have two models that exist in the same environment. You have two different things that need to be quantified. All right, now an appropriate model would have both of those considered. All right, so let's say you had, for example, two models, and we'll call them X and Y for simplicity. So with two models, now of course all of our models are dependent on time, so these would be functions of time. With these two models, say for example x of t and y of t, you would have a system of first order equations, of first order differential equations. You get two simultaneous equations. One of them would be something like the derivative of x with respect to t is equal to some function, I'll call it g1. Now, of course, everything is in terms of time, but since these two models are interacting with each other, this function g1 would depend on time, and it would depend on the information of these two different models, so x and y. These are commas. Like that. And the change in y with respect to time would be some other function of, again, those parameters, t, x, and y, like this, where g1 and g2, for our purposes, are going to be linear and even first order. Where g1 and g2 are, again, this is not a requirement in general, but this is where we're going to look at them. They're going to be linear in x and y and first order. Well, I guess first order means linear, right? Are linear, first order in x and y. By which I mean it would look something like this. G1 of t, x, and y would just be some constant times x plus some other constant times y plus some function of t. Right? It doesn't have to be linear in t specifically, just x and y. So here, this t could be, some other function. It could be quadratic, it could be cubic, whatever. But these would be linear. And likewise, g2 would have the same pattern. G2 of t, x, and y would be something like c3 of x plus c4 of y plus some function, maybe constant, maybe not, of t. Like that. So we have, if both of these are considered simultaneously, this is called a linear system. All right, so if either or both of these differential equations is not linear, then we have a nonlinear system, which we're not going to consider right now, okay? So right now we're looking at just not linear systems. If either of these or both are not linear, that's a different story. Okay? So let's consider an example here. Let's say you have a tank. You say, well, you've done tank problems before. We know how to do those, right? But now let's have two tanks. These tanks are going to be fed from some external source, and they're going to flow out to some external source. However, there is going to be a connection between the two. Here, one tank will feed into the second, and the second will feed back into the first. And hence a relationship between the two, which will necessitate a system for both of these. Okay? So let's say from the external tank we have 3 gallon per minute input of water, and this is just pure water, no additives, nothing, just pure water. So 3 gallons per minute, and this is just water. Okay? Now out we're going to have a flow rate of 3 gallons per minute. Okay, so you're never gonna have a chance for liquid to build up. Right? Whatever's coming into our system is what's going out of our system at the exact same rate. However, this one will not be pure water. It'll be water mixed with whatever was in these tanks. So I'll just say mixture. Okay. Now, we'll call this tank A and tank B because it's nice to have a label to things here. Now, between tank A and tank B, this one, and I don't think I left enough room to write, so I'll put it down here. Suppose tank A contains 50 gallons of water at the start, before we start the system, right? Before we started pumping things in or out, we're starting off with 50 gallons. And that's not pure water. We're going to go ahead and mix some salt in there. So we're going to put in 25 pounds of salt. Okay. Now, tank B is also going to begin with 50 gallons of water, but this one will be pure water. Tank B contains 50 gallons of water. And again, no additives there. That one's pure water. Okay, so now we're going to start up our system. So that's got water and salt. This has just water. Pure water is coming in, and mixture of salt and water is being pumped out. The rate that of the liquid circulating between these two, you're going to pump out 4 gallons per minute from A to B. You say, well, tank A is going to empty out, right? You're pumping in 3 gallons every minute, but you're losing 4. So eventually it'll just drain, right? Well, no, because tank B is going to pump back 1 gallon per minute. One gallon per minute. So this tank is receiving 3 gallons plus 1 gallon, 4 gallons a minute, and it's pumping out 4 gallons a minute. So it's an equilibrium. The amount of liquid is going to remain the same. Here, this tank is receiving 4 gallons every minute and is pumping out 3 plus 1. Oh, so it is also in equilibrium. The amount received is the same as the amount pumped out. So the amount of liquid is going to remain the same. But since there's different concentrations of salt and water in each one, the salt is what we need to keep track of, right? This will stay 50 gallons always. This will stay 50 gallons always. And as a net system, this is gaining 3 gallons per minute and losing 3 gallons a minute. Water will remain consistent throughout, which is nice. Constants are always a nice thing. So now our question is, of course, we want to find a model that describes the amount of salt in our tanks. So that's our question. Find a model. Oops, I don't know how to spell. Model, E-L. I like to joke that I've only been speaking English for about 35 years. I haven't had time to learn it correctly. Find a model that describes the amount of salt in tank A, at any given time t. And likewise, another model for B as well. We'll call the first one x1. And a model that describes the same thing for B. We'll call that one x2. And of course, you could always say x and y, but I'm going to go ahead and go with x1 and x2. Just a personal preference. All right, so here we go. Let's go ahead and start off. Just like with a model of us, just like with a single model, we don't want to start off with anything too complicated. We want to start off with the most general notion that summarizes what we're doing, and then we start adding details. Okay, so rate of change dx1 dt. This tells you, okay, how quickly is the change to tank number 1? Because remember, x1 is telling you what happens to the first tank, to tank A. Okay, well, without putting in any numbers yet, just what's happening to the salt? How is the salt changing here? Well, there's an input rate and there's an output rate. There's a certain amount of salt coming in and there's a certain amount of salt coming out. You say, well, no, there's no salt coming in. Look, it's pure water. Yeah, but there's also this liquid that's coming this way. And this one will contain some salt due to their mixing. Okay, so I do have to consider both. So in general, this is just the input rate of salt into A. Input rate of salt into A. And minus, well, then you got to subtract the output rate. That's coming from A. Okay, well, let's see. What about what is the input rate? Well, there's two inputs. There's things coming from the outside and things coming from the inside. Now, of course, we know the one coming from the outside has no salt, but I'm going to go ahead and put it here anyway, just so that we account for absolutely everything. We don't want to leave anything out, even if it doesn't end up being 0. Okay, so here, just generally, without worrying about numbers, input is from the outside and from tank B. This is input from the outside, and, so plus, right, the input from B. Minus the output rate. Well, there's only one output, and that's from A to B. Output of, from A. From A. All right, so now let's see if we can't quantify these things. The input rate. Well, from the outside source, we have 3 gallons a minute coming in. And each gallon has no salt. So there's 0 pounds per gallon. Now from B, you have 1 gallon a minute coming in. Times, remember it's a rate, so you're multiplying those, times, well, how much salt is in tank B? Well, we can't just give a nice number like 0. We don't actually know. Now, some of you might even think, well, no, you said tank B holds just pure water, right? Yeah, at first, but as the system starts to circulate, it's going to change. Some of this salt's going to come in here, and this will have some concentration of salt. It may be a low concentration, but it is a concentration other than 0. So here we can't just say times 0. Oh, okay, so what is the input from B? Well, it's the concentration of salt in tank B. In tank B, you're going to have a certain number of pounds of salt divided by a certain number of gallons of water. Oh, well, that's consistent. We began by saying these tanks have 50 gallons of water, and because the net input is the same as the net output, you will always have 50 gallons of water. But the amount of salt is unknown. It will change over time. Oh, well, the amount of salt is x2. All right? We don't know what it is yet, but we know that we're going to call it x2. The amount of salt in B is called x2. So that's what we're going to put here. So every minute, you're getting 1 gallon of water coming in, and each of those gallons will have some number over 50 pounds per gallon. We don't know what that number is, but we can at least label it as x2. Okay. Minus, okay, so now we have an output from A. Okay, from A, you're getting 4 gallons a minute. Times, and we pull the same trick. Our concentration of A is going to be some amount of salt per 50 gallons. Now, again, some of you might think, well, it's 25 pounds per 50 gallons. Yeah, at first, but that's going to change very quickly as we start circulating this brine, this salt water. So, yes, the 50 is going to remain constant throughout. That's going to be 50 gallons. But our amount of salt in tank A will change over time. But whatever it changes to, again, we're calling that x1. X1 is what describes the amount of salt in tank A at any given time. So that's going to be X1 pounds of salt for every 50 gallons of water. Sometimes people have a hard time knowing if they've arranged this correctly. One little heuristic, one little quick way of determining whether or not you have put things together at least seemingly correctly. This won't save you from little tiny errors, but it will confirm that you're at least thinking the right way. And that is if your dimensions match up. All right. Pounds per minute. Pounds per minute. Pounds per minute. Yeah, if you add pounds per minute to pounds per minute and subtract pounds per minute, you get pounds per minute. Okay, everything matches up. Everything's in pounds per minute. If some of them were pounds per minute and other ones were gallons per minute and other ones were gallons per pound or whatever, that clearly something's wrong. Right? We can only match things up if they're the same kind of measurement. So here we at least show that, hey, we might have made a little mistake somewhere, but at least we're thinking the right way. So here, 3 times 0 is 0. Okay, so that's going to be 0. For now, I'm going to say pounds per minute. Plus, now here I've got 1 times x2, which is just x2, over 50. And this, again, is pounds per minute. So we're looking 50. There we go. And then minus, and then I've got 4 times x1 over, again, 50. And this is also pounds per minute. And again, this is just a little heuristic to help note, hey, look, pounds per minute, pounds per minute, pounds per minute. If these didn't match up, we're not doing this right. We're not matching up our units correctly, and something is wrong. This doesn't guarantee we're right, but at least it suggests that we're on the right track. We're thinking the right way. Okay? And then, of course, we can simplify. Now, we're going to be solving this as a system of equations, so we're going to leave off our units. Since we know they match, okay, whatever. We just remember everything's in pounds per minute, and we don't bother writing these. So what we have as our model is dx1 dt is equal to, we're going to leave off 0. We're going to have 1 over 50 times x2 minus 4 over 50. I can write that as 2 over 25 x1. 1 over 50 x2 minus 2 over 25 x1. So we have a single equation with 2 variables. Oh, well, that's no good. You can't solve that, right? But that's why it's a system of equations. Here, this is one member of our system. Let's go ahead and find the other member. We're going to do the same thing for the second tank. The rate of change of salt in the second tank, dx squared dt, same idea, except for b now. So now this is the input of salt into, now we're looking at tank B, minus the output from B. Same as before, except A, now it's B. Okay, well the input into B, let's see, where are we getting stuff from? Well, into B, you've got one source. Out of B, you got 2 locations, you got 2 destinations. Okay, so it's going to be different from before. The input into B, there's only one source from that, and that's the input from A. Okay, so this one, we're going to write this as the input from A minus, now our output, there's 2 sources of that. There's going back to A and then going out of the system. Okay, so that's going to be output from B to A and then there's another source of output, and that is output from B to the outside. It's leaving our system. Like that. Okay, now we can put numbers to this. Input from A. Okay, well, coming into B from A, we have a rate of 4 gallons a minute. Okay, so that's going to be 4 gallons per minute. Times, now we have to have a concentration. This is just the liquid, but how much salt is in that 4 gallons per minute? Well, it's the amount that's in A of salt divided by the amount that's in A of water. The amount that's in, the amount of water is 50. It's always going to be 50. The amount of salt from A is x1. So here this is going to be x1 over 50. The amount of water never changes, but the amount of salt does. And we call the amount of salt in tank A, we call that x1. So this is going to be pounds of salt per gallons of water. Minus, okay, now let's take a look at our two outputs. The output from B to A, well, that's going to be 1 gallon per minute from B to A. That's 1 gallon per minute times, and then the concentration of salt, well, that's going to be how much is in B divided by how much salt is in B divided by how much water is in B. That's x2 over 50. x2 is the amount of salt in tank B in pounds, and 50 is the gallons of water in tank B. Plus, and then output from B to the outside, that's 3 gallons a minute. And again, these two are being added because they're both outputs. They're both contributing together to this full set. So that's going to be 3 gallons per minute times the exact same concentration. Because even though they're going to two different locations, the stuff that's being sent there is the same stuff. It's the same concentration. So this one will also be x2 over 50 pounds per gallon. So that's going to give us 4x1 over 50, which, 4x1 over 50, and that's going to be pounds per minute. Then we want to make sure that our units are matching up, and if they're not, something is wrong. Minus, so now here I've got 1x2 over 50 plus another 3x2 over 50. So 1 plus 3, that'll just give me 4. I can combine the like terms. There's 1 of these plus another 3 of these. That's 4 of these. 4x2 over 50. And again, this is in pounds per minute, and this is in pounds per minute. So everything together is in pounds per minute. So since everything's in pounds per minute, we're going to ignore our units, at least until the very end when we say our answer, right? And so here we have a result of dx2 dt is equal to 5 over 50. I can reduce that to 2 over 25 x1 minus, again, 4 over 50. That's 2 over 25 x2. And this would be an equation for the rate of change of the amount of salt in tank 2 per unit of time. So now notice, this is a single equation with two variables. Can't be solved. This is a single equation with two variables. Can't be solved. But together they form a system. So putting these together, we have our system. Thus, our system is dx1 dt is equal to 1 over 50 x2 minus 2 over 25 x1, and dx2. You can use dx and dy, but I've already made this choice, so I'm going to stick with it. dx2 dt is going to be 1 over 25 x1 minus 2 over 25 x2. Like this. Note that with just like the models that we saw in the previous sections, the models themselves come with initial conditions, which will help us to solve for a particular model rather than just a type of model. So here, our initial conditions are already stated. We just have to know where to pick them out. Initially, we're looking for the amount of salt in a system. That's what x1 and x2 represent. So our initial conditions must be the amount of salt that was initially in the tanks. Yes, there's also an initial measurement for water, but that doesn't show up anywhere in our computations, anywhere in our variables. So at best, the numbers that are coming from the gallons of water in our tank are all constants. So we're not solving for those. So here, for our initial conditions, we have that tank A contains 50 pounds of salt at the beginning, and tank B doesn't contain any salt. It's just pure water. So our initial conditions are 25 for the first one and 0 for the second one. With initial conditions x1 at 0 equals 25, and x2 at 0 equals to 0. The amount of salt in the first tank at the very beginning, and the amount of salt in the second tank at the very beginning. And this would be our setup. So that is as far as we can go with this for now. We are going to see how to solve this problem. I will be revisiting this problem again, I believe 3 more times throughout this course. We're going to see how to solve it using a few different techniques as they become appropriate. As we introduce them, we will say, hey, remember that problem? We're going to go ahead and bring that back and use it a few times as an illustration of some different techniques. But for now, that is it for this section. That is it for this illustration of setting up these kinds of models. As always, if you have any questions, please let me know. Otherwise, I hope you all have a nice day.